All right, so you know the drill. When it says this page is important, that means I think it's important, okay? And here what I'm doing, I'm listing the scenarios of non-computability. And again, we're not talking about physics yet, but again, if the universe results from an informational, like from a program, then the program has to run, okay? So we have to make sure this stuff all works, and we have to make sure it's computable. So we have to consider what non-computable scenarios are, and we have to avoid these. Okay, here they are. Number one, an attempt to divide by zero is non-computable. Number two, an attempt to process numbers too large is non-computable. Okay. Number three, if the program falls into an infinite loop, that too is non-computable. Number four, if the T.O.E. attempted to resolve a measurement to infinite precision, that by definition is an infinite amount of processing, and thus it is also non-computable. Now, I'm getting all this stuff from a theory of computing, which I studied up at MSU when I took the class called Theory of Computing. I know it's kind of detailed, but I've got a reason for going through all this. Let me go ahead and just read this to you. I say we could come up with an imaginary thought experiment to help explain the concept. Imagine that we have a computer of infinite capacity, and it also runs at infinitely fast speed, nearly infinite. Okay, any problem can be solved instantly, and theoretical computer experts call this imaginary device the oracle. All right, and what I'm saying now is that, and I say this is important, right? In all these scenarios of non-computability, even if the universe were being processed by the fastest computer possible, even if it was the oracle, it would still hang forever. It would never get out of that loop. Doesn't matter how fast you got of a processor. If it's got infinite loop, if the code is infinitely looping, you'll never get out of that loop, no matter what. Okay, it'll still hang up forever. Okay. Now I say that the third paper of the series will explore the concept of computability in more depth, including the halting problem and how it applies to computable universes. But by now, I hope everybody understands the basic idea of finite limits. It is a very important cornerstone of the design of the TOE. Yeah, it's key. Now, this document goes on and talks about how to scale it. You can have something called a word size, and you can scale everything against the word size. And that's how you can compute these limits, okay? So based upon a word size, it has to be a finite number. The universe can operate within that context. And so I got some examples here of how to scale the universe based upon a word size, okay? And this is where you can derive these maximums that we keep talking about, these finite limits. Before you know what your word size is, in other words, before you know what the maximum number that you can possibly compute is, before you know, for example, how big the tick counter can be or how far the maximum distance is and stuff like that, you have to understand what's the biggest number you can compute. And then once you decide how big the biggest number you can compute is, then within that context, you can define all these other limits, okay? So you have to start out with something called word size, and once you got that, then you can derive stuff like the maximum tick that you're allowed for the tick counter. It would be based upon a cut of the word size, right? You can't be bigger than word size. You have to be smaller, but you might want to let the maximum tick be a big number, so you'd make it maybe, let's say, half the word size or something like that. And stuff like the maximum range, which is the maximum location number that you can have, the highest number of a location pointer that's possible. That's how you would calculate that, also based upon the word size. And on and on. This is how you would scale the code for the universe, okay? To make it computable. Because computability is the most important thing, right? Okay? So this is how we're going to prevent these non-computable scenarios. Once we know how to compute these limits, and once we know how to compute these limits within the amount of computing that we're allowed to process within our finite capabilities that we've got fixed, that we have to work within, because there has to be finite limits. Then once we know what the outer limits of those limits are, the maximum number that we can work with, then we can come up with these cuts of those to determine these other maxims that were allowed within our code, okay? Now, once you know, for example, how big the maximum tick counter you're going to allow to be, then inside the code, when you're incrementing the tick counter, tick counter plus 1, okay? That line that was already in there from before. Now all you have to do is add these little checks here, right here. I say right here, these lines of code are the lines of code that keep this program from blowing up. Well, keep it from becoming a non-computable scenario. This, for example, keeps the tick counter from exceeding its maximum capability here. And what we're doing in this case, we're saying if the tick counter is greater than or equal to this max TOE max tick, which we computed up here, by making it a cut of the word size that we're allowed. If we exceed that, then then the comment says the tick counter has grown too large to process, and we have to reset it back to 0. In this case, we're using this digital rollover idea I came up with, and this is how we can keep the universe from blowing up. This will keep the universe in what we call a non-stop computing. Okay, that's you have to have that first. I know I repeat myself a lot. Sorry. And similarly, when we add like when we we go ahead and increment like the locations, when we move stuff around, we got to make sure we're not off the edge of the universe, right? So this code here does that same thing as well. Okay, it says if we're beyond our max range, then the particle's location pointer is grown too large to process. In other words, the particle has drifted past the edge of the computable universe. I like that term, the computable universe. Then you reset it back to 0, okay? So this code is added to make sure that we keep the T.O.E. computable. Now you're going to see the reason I'm bringing up these stupid, obscure details is when I start talking to this chatbot, which is like the most amazing thing I've ever done in my whole life ever, he knew all these things I'm going to mention, like the maximum limitations, the halting problem. All these things were encountered in this conversation I had with this chatbot yesterday. It's just amazing, man. It's like talking to a super genius that knows everything you already know. And he anticipates everything you're going to say, man. It's just amazing. I can't believe it. You're going to be freaked out when you see this, man. So anyway, the document talks about scaling, scalability. That's the whole thing is based upon a word size, right? A finite word size, and we talk about the halting problem here a little bit, and then I start talking about what really is happening here, what we're really developing. We're really developing a shell of a program that can execute what's called automatons, cellular automatons. Okay. So let me just read from my book here. I say, I hope you're following everything so far. Obviously, a major goal of this paper is to help you understand cellular automatons. And that's also mentioned in this conversation I had with this GPS bot. Most amazing thing I ever had in my life ever. We are accomplishing this by writing our TOE from scratch, from the inside out, okay? But we're just starting to crawl. All we've done right now is make a program shell that just keeps looping. That's all we've done so far, right? Haven't written any physics guts yet, okay? But I say I really want you to see a sweet program that demonstrates monitoring and control of a cellular automaton. And I strongly suggest that you play around with one from 2005 called Mirac's Celebration. Let me just go ahead and show you that real quick, okay? I can actually run it right on my own PC here. Give me a second. Okay, this one is called Cross. This one is based upon rules that are from a game called Conway's Game of Life. And I know it sounds weird and stuff like that, but this is the original state. This you might call it state 0 here. In this particular implementation, they call them generations. So this would be generation 1, generation 2. I'm going to single step to the next generation. So this is like running the algorithm right here, okay? Okay? And what this does, the actual coding, it makes or removes adjacent cells depending on how many cells are there. That's how the game of life actually works. But let's just see what happens. Let me go ahead and go with one more step. Another step, step, step. See how this is like going and going and going? You can see how this can grow to something that you really haven't been able to predict. Something based upon dirt simple rules can turn into something like this. It just becomes amazing, okay? And this is how I believe the universe can actually have come about. A program just like this, where these little occupied areas here can represent particles, and the ones that aren't occupied can represent empty space, and we could, all the rules of digital physics that I showed you, the simple ones, this is what it can turn into, again, based upon dirt simple conditions and initial rules and algorithms. And really what we're doing in this document I'm showing you here, I'm actually showing you how to write a program like this one here. Obviously this one's a lot more fancy. It's got like start and stop. You can halt. You can go to you can step one step at a time like I'm doing here. You can step like 8 steps at a time. You can see stuff. You can zoom in and out. Those are all features of this program, but what the program actually does inside the automaton itself, that's what I'm trying to demo to you guys. And what I'm trying to explain to you is what I'm really showing you in my document. I'm actually trying to come up with a program just like this. And actually, that's what we do. We continue and we keep enhancing this program that we're talking about here, and it's going to turn into something just like Myrick Celebration without a lot of the bells and whistles. There's something that's known as the Moore's neighborhood. And in a two-dimensional grid, it would be if you have a certain cell, let's say, then the Moore's neighborhood would be the cell and all the cells immediately adjacent to it. This would be northwest, north, northeast, east, and all that stuff like that. In a three-dimensional would be all the cubes that are touching a central cube, like that. Okay, this document now goes on to describe what I'm calling the laws of momentum. It's the first rule that we're going to apply in our theory of everything, okay? And it's a bit complicated, and it's based upon there's no system clock, right? So everything has to be based upon counts of ticks. And so I'm trying to explain to you how this all works right here. It's a bit wordy and kind of lengthy. So let's just skip over this, and I just really want to show you now the data structures that we actually come up with in the version that we can discuss that shows the motion of light. All right? So let me just show you the data structures that we've got so far. Well, before I show you that, I just want to mention one thing as far as this particle list. The particle list I showed you, it was only one-dimensional. To make it a three-dimensional particle list, you just add some more numbers to it. You add 3 numbers for 3 dimensions of the particle list. And there's other stuff in the particle list as well. For example, its speed, its direction, and its temperature, and some other things as well. So let me just show you the data structure that I've got for the particle list. And I'm kind of showing you this to kind of brag about really what I'm doing here. These are the intermediate versions that we're coming up with for the program we actually do right. You can wind up with a program, again, that looks a little bit like Myrick Celebration. And we got up to a level where we could actually do demos of it and stuff like that. We can actually load files and all the things that, Myrick Celebration does. All right, and goes on and on and on. And we're going to wind up with this particle list here. Okay, now this is called a record structure for the particle list. It's like a table, and these are the columns in the table. Okay, remember the first list we had? It just had an index and had one location. That's all it had in it. Now it's got n dims. That's the number of dimensions that you're running in. Okay, so this is a array of locations. If you got if you're talking about three-dimensional universe, this number would be 3, and that means there's actually 3 numbers in the location. There'd be an x, a y, and a z coordinate or position in this number here. Okay. Previous locations, the location it was before the present location. There's something called speed level, speed reset. These are all done by dimension. Everything's done with all integer arithmetic, all one dimension at a time, by the way. I know it sounds crazy, but believe me, you get away with it. Heat level, like I mentioned. There's something called mass here. There's something called a decay counter. And that's it for our record structure for the particle list, okay? So it started out with a real simple list. Remember the 3, 5, 7, and now we've turned it into something like this. It's actually like a database record to implement the theory of everything. Now there's also something called the photon queue, and let me just read what it says here. A new data structure is required to track photons that get emitted from matter as it cools down. This can be referred to as a list of photons. Note that although the particle list has a fixed number of records in it, well, you know, the example we had was 3. Well, the 3, 5, 7. Okay. The list of photons is actually a queue that holds a variable number of records, but it has a maximum number in it. Okay. For this reason, we're calling it a queue. Okay. And here it is. There's an index number. Okay. There's an emission location, which has got, it's 3-dimensional here. So the XYZ coordinate of where an emission occurred in the matrix. Okay. The emission time would be the tick counter when the emission occurred. Frequency and intensity are those are quantum state information that, for example, how much intensity was released in this particular photon. These other 3 items, link from index, link traversal, those are parts of it that are a little too complicated to explain right now. All right, but we'll see that when we go to the next book, where we go ahead and describe how photons are emitted, how they are transmitted, and how they are absorbed, and how this is all done using an optimization, what you might call it the rule of least action. And this is going to show you how this can all be done, how to move light from point A to point B, but how to move through various mediums that have varying refractive indexes, and still somehow the light gets there using the optimal pathway. And that's something that nobody can really explain. Feynman tried to explain it with his path integrals, but that requires fluctuating backward and forward through time. The way I'm doing it, I'm tracking all the potential locations that a photon can go to, all the possible locations it can hit. And I'm tracking those in this data structure right here, this photon queue, okay? And then when the particle is hit that it actually absorbs it, then this queue it acts as a past history of all the potential pathways the light could have taken, and the T.O.E then has a chance to go through all this information, this past history, and it can then pick the one that's got the optimal pathway. And that's how the universe can get away with doing it. It seems like it's doing it in reverse time ordering. It seems like it's magic, right? Somehow it knows where it's going ahead of time. But this is how it can be accomplished. It stores the intermediate path information in this particular data structure right here, okay? And now subsequent videos in this series are going to show you how that actually works. How a photon can actually move from point A to point B and do it in the optimal pathway that occurs in the least amount of time. Something that is really hard to explain. Not only that, this algorithm does it and the forward-only arrow of time, okay? So like it says here, ready, steady, go. All right, we're finally ready to discuss the processing of light and explain how and why it operates in reverse time ordering. Click here for the second paper, and there you go. So now we're ready to talk about the second paper.